Next chapter is refraction by the eye. So the thin lens formula, which is discussed in chapter 5, it is inadequate to deal with the refracting system of the eye. The refracting system of the eye is composed of a number of refracting surfaces, and they are separated by relatively long distances. The theory and formula of refraction by thick lenses can be directly applied to the eye. So refraction by thick lenses is therefore considered now, and the principles are subsequently applied to the eye. So now the thick lens theory. So in thick lens theory, first there are cardinal points of a thick lens which should be understood. So the thin lens, which we have discussed in the previous chapter, it ignores this lens thickness and only considers refraction at the two lens surfaces. And this thick lens, this approach is invalidated by the greater separation of the two refracting surfaces by lens substance. The lens substance separate this refracting surfaces. So there are principal points and principal planes. These are hypothetical planes. The principal points and principal planes, these are hypothetical planes and they are hypothetical points, such that a ray incident at the first principal point, this is first principal point, or first principal point or plane, this is P1, it leaves the second principal point or plane P2 at the same vertical distance from the principal axis. This is principal axis. The exact position of the principal point, is calculated from the curvature of the lens surface and the lens thickness and the refractive index of the lens material. It will tell us the exact position of the principal point. The principal planes intersect the principal axis here at right angle at the principal points. There are two further points called the nodal points N1 and N2, which correspond to the center of the thin lens. So any ray directed towards the first nodal point N1 leaves the lens as if from the second nodal point N2 and parallel with its original direction. So it is undeviated. When the medium on both sides of the thick lens is the same, then the nodal points coincide with the principal points. When the media on the opposite sides of the lens are different, then the nodal points do not coincide with the principal points. The principal foci f1 and f2 have the same meaning as for the thin lens in chapter 5. The focal length f1 and f2 being measured from the principal points, which we will discuss. Next is vortex power and equivalent power of thick lenses. So this figure shows that the principal points do not lie on the surface of the lens. They may lie within the lens, or in meniscus form lenses they are outside the lens substance. In practice, the measurement given by the instruments such as focimeter is the distance of the principal focus from the central surface or vertex of the lens. So the distance of the principal focus from the central surface or vertex of the lens. The distance is the anterior, this is anterior or posterior vertex focal length, anterior or posterior vertex focal length, AVFL and PVFL, and it must be distinguished from the focal length F1 and F2. Furthermore, note that the anterior and posterior vertex focal length are not equal to each other. They are not equal to each other. So they are not equal to each other. Here you can see. The reciprocal of the posterior vertex focal length. The reciprocal of this posterior vertex focal length, if expressed in meters, is the posterior vertex power. So the reciprocal of this is the posterior vertex power. Posterior vertex power expressed in diopters. An alternative term is the back vertex power. This value differs from the true focal power or equivalent power of the lens. So what is equivalent power? The equivalent power of a thick lens is calculated from the two surface powers plus correction for Vergen's change due to this lens thickness. So the discrepancy between equivalent power and back vertex power, it may be a cause of error in dispensing high-powered spectacle lenses or highly curved contact lenses. However, lens manufacturers and dispensing opticians are aware of this problem, and mathematical tables exist which allow the appropriate adjustment to be made. Spectacle lenses are graded by their back vertex power, as it is their posterior vertex focal length which is relevant to the correction of optical defects in the eye. The second principal focus of the lens. Second principal focus of the lens must correspond to the far point of the eye if a clear retinal image is to be formed. This is fully explained and illustrated in chapter 10. Back vertex power should not be confused with back vertex distance, which is the back vertex distance is merely the distance between the eye and the back vertex of a spectacle lens. Refraction by the eye. The foregoing analysis of refraction by thick lens is just one application of the Gaussian theory of cardinal points. The theory may be applied to any system of coaxial spherical reflecting surfaces, including the human eye. There are three major refracting interfaces to be considered in the eye: the anterior corneal surface and the two surfaces of the lens. The effect of posterior corneal surface is very small compared with these three, as the difference in refractive index between the corneal stroma and the aqueous is not large. The corneal stroma and the aqueous is not large, is shown in this table. The refractive index of the transparent media of the eye. So this is the refractive index. The air refractive index is considered as 1. Cornea 1.376. Aqueous humor 336. Vitreous is also 336. Lens cortex 368. Lens core is increased to 406. So cortex to core, there is a change from 368 to 406. In order to calculate the cardinal points, the radii of curvature, this is the radii of curvature, the distance separating the refracting surfaces must also be known. These have been determined experimentally by several observers. As in the case of any anatomical measurement, there is some physiological variation and the values given are the means. The results of Gould's trend are given here in table 9.1, 2 and 9.3. As it is on these that the given calculations of the schematic and the reduced eye are based. These measurements are known as the optical constants of the eye. However, there are several other set of measurements available from other observers which differ slightly from one another. No one set is in general standard use. So this is the table of the position of refracting surface of the eye in millimeter behind the anterior corneal surface by Gould's trend. Cornea and anterior surface is considered as 0 millimeter, and cornea posterior surface is 0.5 millimeter behind the anterior corneal surface. Lens anterior surface is 3.6 millimeter behind the anterior corneal surface. Posterior surface of the lens is 7.2 millimeter behind the anterior corneal surface. The lens core anterior surface is 4.1 millimeter behind the anterior corneal surface. Lens core and posterior surface of the lens core is 6.5 millimeter behind the anterior corneal surface. These are the radii of curvature of refracting surfaces of the eye in millimeter by Gould's trend. The radii of curvature of the cornea anterior surface is 7.7 millimeter. The radius of curvature of the posterior surface of the cornea is 6.8 millimeter. The lens anterior surface radius of curvature is 10 millimeter. The lens posterior surface of curvature is -6 or 6 millimeter. Lens core anterior surface 7.9, lens core posterior surface 5.7 millimeter radius of curvature. The schematic eye. In the schematic eye, as described by Gould's trend, the refracting system is expressed in terms of its cardinal points, measured in millimeter behind the anterior corneal surface in this table. So schematic eye, these are the cardinal points, distance in millimeter behind the anterior corneal surface by Gould's trend. The first principal point, P1, is 1.35 millimeter behind the anterior corneal surface. So this is the first principal point, 1.35 millimeter behind the anterior corneal surface. Second principal point, 1.6 millimeter. P1 1.35 millimeter, P2 1.6 millimeter. First nodal point 7.08 millimeter. Second nodal point 7.08 and 7.3 millimeter. First focal point -15.7, second focal point 24.4, -15.7, this is 24.4 millimeter. Refractive power of the eye is, total eye is +58.64 diopter, calculated by Percival in 1928. Note that the nodal points via which rays of light are pass undeviated are removed from the principal points which lie at the intersection of the principal planes with the principal axis. This is because the refracting media on each side of the refracting system of the eye are different. Namely, air, the refractive index is 1 and the vitreous 1.336. The nodal points straddle the posterior pole of the crystalline lens. The nodal points straddle the posterior pole of the crystalline lens. The pupil of the eye allows only a relatively small para-axial pencil of light to enter the eye. Such para-axial rays are refracted and concentrated through the nodal points and adjacent posterior lens substance. Therefore, even a small posterior polar cataract produces gross impairment of vision when the pupil is small. The reduced eye. Matters were simplified further by listing in 1853, who chose a single principal point lying midway between the two principal points of the schematic eye. A single nodal point was postulated in the same way, and the focal length adjusted with reference to the new principal point. So, in which the eye is treated as a single refracting surface with a power of 58.6. So in this table, the results of the reduced eye are listed. Many sets of figures exist for the reduced eye. Those quoted here are based on Gulstrand data. It must emphasize that the distance given for the focal points are measured from the interior coordinate surface. So this table shows the reduced eye distances in millimeter behind the interior coordinate surface. Principal point is 1.35 millimeter, while in the Gulstrand it was also 1.35 millimeter. The nodal point is 7.08, the first focal point 15.7, second is 24.13 millimeter. The corresponding focal lengths measured from the principal point are minus 17.05 millimeter and 22.78 millimeter. Note that the nodal point lies in the posterior part of the lens, while the second focal point lies 24 millimeter behind the cornea on the retina of the normal eye. Nodal point in the posterior part of the lens, second focal point on the retina of the normal eye. The students are advised to commit the values to memory because these values and the form of the reduced eye is used in all subsequent discussions of the optics of the eye. The anterior focal length of the aphakic eye was found experimentally to be minus 23.23 millimeter. This gives a calculated power of 43 diopter plus 43 diopter for the aphakic eye. The crystalline lens thus has an effective power of plus 15 diopter. This is the difference between the power of phakic and aphakic eye. 58 minus 43. The actual power of crystalline lens taken in isolation from the other refractive elements of the eye is given by Gulstrand as plus 19 diopter. Discrepancy results from the fact that in vivo the lens is only one element in a larger refracting system. The cornea is only refracting element remaining in the aphakic eye. It has a power of 43 diopter, 3 times as powerful as the crystalline lens in the intact eye. The relatively greater power of the cornea is due to the greater difference in the refractive index between air, which is 1, and a cornea, which is 1.376, as compared with the aqueous and vitreous humor, which is 1.336 and 1.406. 1.336 vitreous humor, lens 1.406. So a difference of 0.376 is opposed to 0.140. Now, a dramatic example of the importance of air-cornea interface occurs when a swimmer opens his eyes underwater. He finds his vision is blurred. The refractive index in the difference in the refractive index between water and cornea is only 0.04, because the cornea is 1.376, water is 1.336. This problem is eliminated by the swimmer keeping air in front of the cornea by wearing goggles. Now, construction of retinal image, reduced eye. Using the reduced eye is represented by two parallel lines, P for the principal plane and R for the retina. So using this reduced eye, it is simple to construct retinal image formed under various conditions. These P and R intersect the principal axis at right angles. The nodal point N is indicated by a point, as is the anterior focus FA. The second principal focus F2 falls on the retina in the emmetrope eye. Two rays are used to construct the image formed by parallel light incident upon the eye. The first ray passing through the anterior focus FA, which after refraction at the principal plane P continues parallel to the principal axis. The second ray passing through the nodal point N undeviated. The size of the retinal image may also be calculated from the same construction. It can be seen from this figure that light subtend angle alpha at the nodal point, as well as at the anterior focus. The retinal image size is therefore directly related to the angle subtended by an object at the nodal point, F1 being the constant in the individual eye, because tangent alpha is equal to h divided by this F1. The retinal image size is tangent alpha multiply F1. Tangent alpha multiply F1. The angle alpha subtended by an object at the nodal point is called the visual angle. It will be appreciated that as an object of given size approaches the eye, it subtends a greater visual angle and thus appears larger. Variable states of emmetropia. In the emmetrope eye, the second principal focus falls on the retina. Parallel incident light is therefore focused on the retina without accommodative effort. The emmetropic state is compatible with the range of refractive powers if the axial length of the eye is appropriate to the dioptric power. Accommodation of the eye. If the refractive power of an emmetrope eye were fixed and unalterable, only subjects at infinity would be clearly seen. Light from the near objects would be brought to a focus beyond the second principal focus f2, and no clear image would be formed on the retina. This problem is overcome by the ability of the eye to increase its dioptric power. The crystalline lens is held suspended under tension by the suspensory ligament which attaches it to the ring of ciliary muscle. Ciliary muscle contraction reduces the tension on the suspensory ligament and the lens. Allow the lens to assume a more globular shape. Here it can be seen in this figure. The curvature of the lens surface and the lens thickness are increased, and thus the dioptric power is increased. Most of the change in curvature occurs at the interior lens surface, which moves forward slightly towards the cornea. The ability of the eye to increase its dioptric power is called accommodation. Before analyzing this process of accommodation further, it is necessary to define certain terms. The far point of the distant vision is the position of an object such that its image falls in the retina in the relaxed eye, in the absence of accommodation. Far point in the emmetropic eye is at infinity. The near point of a distinct vision is the nearest point at which an object can be clearly seen when maximum accommodation is used. Far point of in different states: myopia, it will be in front of the eye, and emmetropia at infinity. Hyperopia, it is virtually behind the retina. The distance of the far point from the principal plane of the eye is denoted by r. This is r, which according to sign convention carries a negative sign in front of the principal plane and a positive sign behind the principal plane. The range of accommodation is the distance between the far point and the near point. So normal vision, myopia, hyperopia, and presbyopia. This is at infinity, and this is 30 centimeter. Amplitude of accommodation is the difference in dioptric power between the eye at rest and fully accommodated eye. The dioptric power of the resting eye is called static refraction. The dioptric power of the accommodating eye is called as dynamic refraction. The amplitude of accommodation is given by the formula P minus R. A is the amplitude accommodation in diopter. P is the dioptric power of the value of the near point distance. R is the dioptric value of the far point distance. Applying the formula to the case of emmetropic eye with 10 cm near point, amplitude is 10 diopter. To calculate the accommodative power required to focus a point within the range of accommodation, then we have the formula V minus R. A is the accommodation power required, V is the dioptric power value of the intermediate point, R is the dioptric value of the far point. For example, to focus an object at 50 cm, the emmetropic eye must exert 2 diopter accommodative power. The amplitude of accommodation declines with advancing age, giving rise to condition of presbyopia, inability to focus near objects. So how this 10 diopter comes? 10 diopter is the reciprocal of 0.1 meter. It is the case of emmetropic eye with the near point of 10 centimeter. 10 centimeter mean 0.1 meter. the reciprocal of 0.1 meter is 10 diopter. So the amplitude of accommodation can be calculated from the reciprocal of near and far point distance. So if the near point distance is 10 centimeter, so the reciprocal of 10 centimeter is 10 centimeter, or 0.1 meter is 10 diopter. And the reciprocal of, so here P is 10 diopter, and R is, the reciprocal of infinity is 0. So 10 minus 0 is 10 diopter. So again, to calculate P can be calculated from the reciprocal of near point, which is 10 centimeter, or 0.1 meter. The reciprocal of 0.1 meter is 10 diopter. So here put 10 diopter in P, and R is the reciprocal, can be calculated by the reciprocal of infinity, which is 0. So accommodation is 10 diopter. So suppose to calculate at 50 centimeter, so 50 centimeter, the reciprocal is R 0.5 meter. The reciprocal is 2 diopter, while put 0 instead of R, so 2 minus 0 is 2 diopter. To focus is at 50 centimeter. To focus at 1 meter, the image rope must exert 1 diopter of accommodation power. This topic is accommodative convergence to accommodation ratio, AC divided by A ratio. In order to view a near object, the eyes must not only accommodate to ensure clear retinal image, but also the eye must converge to maintain binocular single vision. The two functions, the accommodation and convergence, are strongly linked, and the number of prism diopter of convergence which accompanies each diopter of accommodation is the AC divided by A ratio. It is constant for each individual, and the normal AC divided by A ratio is 3:1 to 5:1. The AC divided by A ratio may be measured by various methods, and one of the more accurate being is the heteroporia method. This measures the ocular deviation for distance and near with full spectacle correction. Hence the formula is AC divided by A is equal to IPD. IPD is the interpupillary distance, a distance in centimeters, plus N is the working distance at near in meters, and so D dash is the near poria, D is the distance poria, or T dash is the ocular deviation at near, and D is the ocular deviation at distance. By convention, a positive value denotes an isodeviation and a negative value an exodeviation. The ratio may also be measured by the gradient method, which use a minus lens rather than a near object to stimulate accommodation. Calculated values are less than and possibly more accurate than those calculated by the heteroporia method. So here N is the power of minus lens, D dash near poria, distance poria, and N is the power of minus lens used to induce accommodation. Calculated values are less than and more accurate than those calculated by heteroporia method. High AC divided by A ratio is betrayed by much large angle of isotropia for near than for distance. So in clinical practice, Abnormally high AC to A ratio is betrayed by a much larger angle of isotropia for near than far distance. Convergence axis isotropia, in which the eyes are straight for a distance but break down to a convergent squint for near. So it is important to distinguish this condition from esotropia, that is similar for near and distance, because the optical and surgical management differs. In convergence axis esotropia may be controlled with bifocal spectacles. Convergence axis esotropia may be controlled with bifocal spectacles. The distant portion incorporating the full hypermetropic distance correction, and the near portion have further plus power so that little or no accommodation is required for near, and binocular near vision is facilitated. If surgery is appropriate for convergence axis esotropia, recession of both medial recti, and for esotropia without convergence axis, recession of one medial rectus with resection of the ipsilateral lateral rectus.